Hello, this is 5.1. It is, this chapter is on integral calculus. So we're going to start by estimating areas under curves. And this first example says a bullet leaves the barrel of a .22 rifle at 1,200 feet per second. Assuming a constant velocity, how far does it travel in the first 2 seconds? Now I realize you could solve this problem very quickly using distance, rate, and time. But the question is, can you also use a graph to answer the question? I'd like you to pause and see if you can figure out how you would answer this using a graph. Okay, so now I'm going to show how to do this. So we're going to have a graph, and the two quantities that are given are velocity and time. So we will put time on the x-axis. In this case, it's in seconds. And then the logical place to put the velocity would be here. Whoops, not 1,200. Velocity would go on the y-axis, and the units are feet per second. Now it is a constant velocity, so that's going to be a horizontal line at, 1,200, and it's traveling for 2 seconds, so 1 and 2. Okay, now I have a graph. How am I going to use this graph to answer the question? Well, notice the units on the axes. I've got feet per second and seconds. And what happens if I multiply feet per second times seconds? Well, I get feet, which is the units of distance, which is what we're trying to find. We're trying to find how far. So sure enough, we're going to be multiplying it. When we multiply, by the way, I'm going to drop this down here. What I'm multiplying, I'm basically multiplying the length times the width. So I'm finding the area under the curve is how we say that. So you've got the height is 1,200 feet per second times the length, which is 2 seconds. And then those will cancel, and you get 2,400 feet. So what I've just done then is I have found the distance by finding the area under the velocity curve over that unit, that time interval. And then that's summarized here in the box. Anytime you find the area under a velocity graph with respect to time, that will give you the total distance traveled over that time interval. We need to specify that, over the given time interval. That's very important, actually. So what information can be gleaned from calculating the area under a time acceleration graph? Oh, okay. So let's figure it out. Let's graph it. So we've got time down here, acceleration. What are the units of acceleration? Let's say our time is in seconds. Let's use metric. So acceleration would be meters per second squared. And it doesn't really matter what the acceleration curve is. So when we, I'll just make one up. Let's do that, I guess. Constant acceleration. If we find the area under the curve again, it's going to be acceleration times time, and that's going to give us meters per second. So meters per second would be velocity. Unit analysis is really helpful, and drawing pictures, of course, always helpful. So this is a really important statement. The area under a rate of change curve is the amount of change. So like with the velocity, the rate of change would be the rate of change of distance. And so the area under that would be the change in the distance. Next example. We have velocity on the y-axis again, time on the x, and someone has recorded the velocity of a particle, and they've got this nice smooth curve. We are going to estimate the distance, because we already know the distance is going to be the area under the curve, that the particle is going to travel between hours 1 and 3. So that has been shown here on the x-axis 1 to 3. And someone has already put in the rectangles. And that's exactly what we're going to do. We're going to use rectangles to estimate the area, because we don't have geometric formulas for the curve. There are several different types of rectangles you can use. One is LRAM. L meaning the left-handed. RAM is the rectangular approximation method. So it's a left-handed rectangular approximation method. They're also known as Riemann sums. Riemann figured this out some time ago. I suppose we could research and figure out exactly all the history behind it. So there's also RRAM for right hand, and there's MRAM for the midpoints of the rectangle. So if you look up here, I've got this person has some red rectangles and some bluish rectangles. And which one is which? Well, what you want to do is look down here at your time interval. So I've got a time interval from 1 to 1.5. On that interval, if I start on the left-hand side at 1 and I come straight up and I hit the curve and then I come across and draw a rectangle, that's my LRAM, or it's going to contribute to my LRAM. Because on the left-hand side of this interval at 1, if you come up, that's where it's hitting the curve. And so if you look at all the red ones, so then at 1.5, that's the left-hand bound of the next rectangle. If you come straight up the curve and come across, you're going to have that red one. I suppose I should use red. Of course, it never works. No, it's not going to, is it? It's not going to switch. There we go. And then at 2, you come straight up, you come across, there's the red one. At 2.5, you go straight up, come across, you get the red ones. So the red ones are the LRAM. And then the blue ones are RRAM, because on the first rectangle, 1.5 would be the right-hand side, and if I came straight up the curve and got to the curve, I would have to draw my rectangle to the left in order to fill in that first rectangle. And so that one's going to be RRAM. So the blues are RRAM. And then our job is simply to find the areas of, so if I want to do LRAM, I need to find the areas of each of the red rectangles and add them up, and that'll be my estimate. Okay, I'm going to erase here, and then we'll go ahead and do that. Okay, so I'm doing our LRAM, which is red, so I'm in red on a red pen. The first thing you need to do, or the simplest thing to do, is to figure out the widths of your intervals. Now on this problem it's pretty obvious that it's 0.5, but there is a formula you can use if it's more complicated. We're finding the area from 1 to 3. Think of 1 as your A and 3 as your B. So we're on the interval from A to B. And what you would do, this is going to be delta x, the change for each rectangle, is going to be b minus a divided by how many subintervals you have. In this case, there are 4 rectangles, so, and oh, by the way, that's called n. So n is the number of intervals or subintervals. So this is a handy little formula. You want to keep that in mind, and you'll be using that. On this one, we don't have to because it's just 0.5. So every single one of these rectangles' widths is 0.5, and obviously the area for the rectangle's width times height. Since I'm multiplying them all by 0.5, I'm simply going to pull out the 0.5, so to speak, and put it out in front so I don't have to multiply every single height to it. So now all I have to do is sum up the heights of my red rectangles. Now we don't have an actual function equation for this, so we're going to just guess by looking at the graph. So red rectangle, the first one is going to be about, we could say 5 to make it easy. If you want to be more specific, oh heck, I'll do 4.9, what the heck. Okay, and then we're going to add up the next one at 1.5. I'm going to come up, and here's the top of that one. That looks like about 5.5. The next one, I'm going to come up, hit the curve, and come across. That one's also about 5. And then the last one is here. I'm going to come up, I'm going to come across, and that's about 4. So we'll go to the calculator to make it faster. I've got 4.9 plus 10.5 plus 4. Okay, 19.4 times 5.5 is 9.7, about. It's an approximation. The units are miles per hour times hours, which will end up being miles. And so, and that's good because it's supposed to be a distance. Okay, I'm going to switch to blue. And we'll do our RAM. So again, the width of each rectangle is 0.5, and then I just need my heights from the right-hand sides of these. So on this one, I'm going to come up. That one's about 5.5. The second rectangle is at about 5. Third rectangle is at about 4. And the fourth rectangle is about 4 also. Oh, wait a minute. Oh, yeah. The the right-hand side is at 4. Yeah, it's on 4 on both of these about. Okay, that makes sense. So we've got on that one, we'll add these up, about 9.25. Oops, yeah. And on this one, it does look like our RAM would give you, let me see here. I'm going to clear off some of this. Oh, I can't do that. That's a bad idea. Never mind. Okay, you might want to kind of look at your answer and see if it makes sense. Anyway, let's move on. Okay, this is just a box summarizing what we've just been doing. And obviously, yeah, if you want to get a better estimate, you're going to need more rectangles. And here are the 3 that I just talked about. Example 2, estimate the area under the graph. Okay, so let's graph this. Why is it doing that? Okay, there we go. On. I need to change to radian mode. Okay, we're in radian mode. Y equals x squared sine of x. I'm going to do zoom 7, my trig window there. Okay, we are estimating the area on the interval 0 to 3. So, maybe what I'll do, let's do this since I'm going from 0 to 3. I'm going to change my x min to 0, my x max to 3. That's way better. Okay, so now I'm going to do a quick sketch of this. Okay, so it looks like essentially like that. 0 to 3. And this is x squared sine of x. I highly recommend drawing a picture so that you can put your rectangles on there. We are on the interval 0 to 3. We're going to have 6 intervals. So I'm going to divide it in half and then divide it into thirds. Okay. And it doesn't say which type of rectangles, so we can choose. I'm just going to pick our RAM, just randomly. If you want extra practice, you can choose other ones, and there is a calculator program that hopefully you have, and then you could check your work. So let's draw pictures. So our RAM, I'm going to go to the right-hand side. I'm going to go up and form little rectangles. So right hand over, right over, right over, right over, and this one barely comes up at all. Okay. Then we need to figure out our intervals. I'm just going to use the little formula just so you get practice with that. So change in x is 3 minus 0 divided by 6, so it's 1/2. So this is going to be 1/2, 1, 1.5, 2, 2.5. I realize you could have easily done that without my little formula. Now we are going to go ahead and do the RAM. So it's going to be, so I'll say area is approximately the width, which is 0.5. I like to pull that out front, and then we'll just do all of our y values. So this time we have a function, my I'm doing RAM, so my first x value is going to be 1/2, because that's on the right-hand side of the first rectangle. So I'm going to be plugging 1/2 into my function. So I'm going to have 1/2 squared sine of 1/2 plus, then we're going to do 1 as the next one. So 1 squared sine of 1 plus 1.5 squared sine of 1.5 plus 2 squared sine of 2 plus 2.5 squared sine of 2.5, and then plus 3 squared sine of 3. We have 6 rectangles, so we should have 6 terms here in our sum. 1, 2, 3, 4, 5, 6. It is a good idea to check and make sure you have the correct number. Also notice when I set it up, I didn't actually do any of the simplifying in my head. I just put it all out there. I realized some of this you could do in your head. I find it helpful if you would please set it up like I did so I can check your work and see that you have it set up correctly. Then you have a choice. You can simplify it a little bit, or you could put it all in your calculator and see what the sum is. I'll let you do it whichever way you want. I'm just going to save time, I will look here in my notes. Hopefully I did this one this way in my notes. RAM. Okay, in my notes here I have that it is approximately 5.927. By the way, if you use LRAM, the height of your first one, your first x is 0. So you would have 0.5 and you'd have 0 squared sine of 0 plus, and then you'd have 1/2 squared sine of 1/2, and on down the line. And then at the very end, your last x value is actually just going to be 2.5, because when you do your last rectangle, it's based on the 2.5, not the 3. So I probably should have done the other ones in there. So let me put them all in there, and there's a reason I want to do that. Sorry. So I'll just do that real quick. Okay. So I've got what? Sine 1/2 plus 1 squared sine of 1 plus 1.5 squared sine of 1.5 plus 2 squared sine of 2 plus 2.5 squared sine of 2.5. Count them up. How many terms do you have? 1, 2, 3, 4, 5, 6. Notice the first one is actually going to give you a 0. So there are really only 5 rectangles that are contributing to the area if you do LRAM. And if you do LRAM, you should end up with 5.292. So now, I can't show you the program because I'm not there with you guys. We'll have to show you the program in class because it's not on this computer, on my calculator. I'll have to show you in person. So there is a way to check these, and you do need that program and you need to know how to use it. Okay, moving along. Example 3. We are going to estimate the volume of a sphere. And now I realize this is a lot of work for something we already have a formula for. But it's kind of cool, and you get to see how calculus can be used. And then later on, we're going to actually calculate the volume of a sphere using calculus, not the geometry formula. But that'll be a little later. So first of all, I've got a sphere of radius 4, and we're going to use cylindrical slices. So what we're going to do is graph a cross-section of the sphere at kind of the middle, that would pass through the midpoint of the sphere. So in other words, with a radius of 4, so I'm going to attempt to draw a nice little circle through these as best I can. And okay, we are going to slice using 8 slices, so that's nice because I can just go right down through. The widths will be 1. And that one's right there. And we're going to be finding the volume. So what I want you to do is imagine this is a cross-section of a sphere, and if I slice it like this, I could estimate it by using disks. So let's do, how about LRAM? So over here on the very left-hand side of this rectangle, I'm going to be, well, actually this one won't have a height, will it? So, because it's going to be at 0. Then this next one will come up. This will be the height of it. And down here it'll go like that. Imagine that as a cylinder, because this, kind of think of this circle being revolved around the x-axis, and this is kind of like, this is like dumbbells. And then this one's going to be here. And I'm doing LRAM. Well, now I'm kind of using the red one, the red circle. And this one's here. That one's there. See how on the right here they stick out? Oh, that one should have stuck out above. On the right they should stick out, give an overestimate. And on the left side of this, they're kind of giving an underestimate. So hopefully they'll average out to a nice estimate. Well, what we're summing is we are actually summing the volumes of those cylindrical disks. So this disk here, like if I pull it out, I'm hoping you can visualize this. So I've got these cylindrical disks, and then the x-axis runs through there like that. How do you find the volume of a cylinder? Well, it's pi r squared h. And the h is this dimension here, and for us, that width is 1 unit. So h is 1. And pi is a constant. And the r is the radius of the disk. Well, the radius of the disk is, if you look here, like say this one here would be from the x-axis up to the function. So the height or the radius is the function. That's going to be f of x, which is, oh, we have to figure that out, don't we? Well, it's going to be the equation of the circle. So this circle, since it has a radius of 4 and it's centered at the origin, is going to be x squared plus y squared equals 4 squared, or 16. But we want the y, so if you solve that, you'll get 16 minus x squared, and then the square root. I only need the positive square root because I'm going to just use the top radius. Sorry. So that's the square root of 16 minus x squared. Great, so now we can go ahead and do our sums. So what I'm doing here is I'm summing the cylindrical volumes. And the volume of the cylinder is pi r squared h. Now, I've got a pi, and my h is going to stay constant because they all have a width of 1. So I'm going to pull out 1 pi out front, or just pi in this case, and all I'm going to be summing are the r squareds. So the r is the same as the y. We saw that over here on my picture here. F of x, that is your r. The r is f of x. So I'm going to be putting in my r's and squaring them. So the r is the square root of 16 minus x squared. Now my first x is negative 4, because I'm doing LRAM. So I've got 16 minus x squared, but this is, I'm summing r squared, so this is actually all squared as well. And that's really nice because the square undoes the square root. So really all I have is 16 minus negative 4 squared. And that's going to be the case with all these, so I don't need the square of the square root. I can just skip it. Okay, and then the next one is going to be 16 minus the next x. I'm doing LRAM, so that's -3 plus, and then the next one, 16 minus -2 squared plus 16 minus -1 squared plus 16 minus 0 squared plus 16 minus 1 squared plus 16 minus 2 squared plus 16 minus 3 squared. And do we have a 4 squared? No, we don't, because that very last rectangle, its left-hand side is at x equals 3. We should have 8 altogether, 8 terms, so 1, 2, 3, 4, 5, 6, 7, 8. We've got them all. Another thing you could have done, notice there's a 16 in every single one of these. You could have done 16 times 8 and pulled that out up front as well. In fact, I think I'll do that. So I've got 16 times 8 times pi, and then I've just got, and I'm summing up all these negatives, minus, and so on, dot, plus, da da da, up to the last one. So if you crunch all the numbers, and I did this ahead of time, yes I did, thank goodness, I got 84 pi, 263.894 units cubed. That's with LRAM. If you try this again and do it with MRAM, I'll just tell you what I got. I got about 270.177 units cubed. And it doesn't look like I've done it with RRAM yet. Now it does say calculate the actual volume and find the percent error. Change to blue. So the actual volume is 4/3 pi r cubed. So that's 4/3 pi, the radius is 4, so 4 cubed. And if you calculate that, I've got that, it's 268.083. Then to get the percent error, we'll subtract and divide by the original. Do that down here. So that's going to be, 268.083 minus my estimate, which is right here, 263.894 divided by the actual. And when I calculated this, I got 0.781%. So less than 1% error. It's not too bad for 8 rectangles. And I can show you in class how to check it on that program, and that's worth doing because it's a tad bit tricky to enter. Okay, I have 4 minutes. So, because I'm on my prep, it ends in 4 minutes. I could probably start this a little bit. Let me look at this. Yeah, this is the last example. I'm going to stop it and do it on a separate, I guess I could try to do it in 4 minutes. I don't know if I can do it though. We'll try. This is an example in the book. It's pretty classic problem. A doctor's injecting 5.6 milligrams of dye into the main vein near the heart, and then they measure the dye concentration every few seconds, and it helps, I don't know, some kind of medical thing it helps you with anyway. So, I guess it helps with cardiac output, duh. Cardiac output is, so the units are liters per second. How many liters per second is your heart pumping? Now, you do have to look in the book at this one because they have the data collected there, and it's too detailed for me to put it up here. It essentially looks like that. It has time here in seconds. It has dye concentration in milligrams per liter. This is the dye concentration. And then we'll be looking at the book to get these specific heights of that on that curve. And this is like 31 seconds here. 0. So on that graph, if you were finding the area under this curve, what would the units of the area be? Well, we do the same thing. We do length times height, or height times width. So the height is in milligrams per liter, and the width is in seconds. So the units are milligrams seconds per liter. And we want to find cardiac output, so we want liters per second. This is what we want. And this is what we know. Well, we will know this once we sum it up using the RRAM or LRAM or whatever we choose. So what do we have to do to get from the area to the cardiac output? Well, you could probably see that they are reciprocals of each other somewhat. Plus there's that milligrams in there as well. So cardiac output is going to have to equal the reciprocal of area. So 1 over the area, which will be 1 over, actually, let's just do the reciprocal of area, the units. So what I'm doing right now, I'm doing a unit analysis. So if I do the reciprocal of the units on area, I'm going to have liters over milligram seconds. Okay, that's what I get. Those are the units I get if I do the reciprocal of area. Well, that's getting pretty close to liters per second, but I've got to get rid of the milligrams. So using dimensional analysis, I would need to multiply that by milligrams. So in summary, this part, the L over milligram per second, is 1 over the area, times, I have to multiply by milligrams. So in other words, I'm going to do milligrams divided by area. And that's going to give me the cardiac output. And I'm out of time, so I'll have to make a separate little quick video. We're going to end up doing this last one. We're actually going to estimate the cardiac output and give the answer. So that'll have to come in a separate video.